Next talk is by Pranav Kukreti on a Gaussian life cycle of radio galaxies.
Okay.
Okay.
Hello, everyone. I'm Pranav Kukreti. I'm a postdoc at Heidelberg University. And continuing with the theme of the day, I'll talk about radio AGN and their life cycle and the feedback and what links can we find between the two. So Francesco and Beatrice have already given a nice introduction to the life cycle aspect of radio AGN, but I'll go in a little bit more detail. We know a unique thing about radio AGN is that because of the physical scales of the emission and the spectrum of the emission that we observe, it's possible to time the emission. It's possible to get ages of the emission. And that makes it possible to understand the timescales on which the activity has happened, which can be done over hundreds of million years. And that's quite unique to radio AGN. So from decades of morphological and spectral information, what we broadly understand about the radio AGN life cycle is that once the jets are born, newborn jets, these are compact, bright, and in their spectrum, quite often they have an absorption. That's likely mostly due to the synchrotron self-absorption, the very high brightness temperatures. If you look at that in the radio spectrum, you see the signatures you see is an absorbed radio spectrum, both optically thin and thick emission. Of course, as the source grows to larger sizes, the peak shifts to very low frequencies beyond our lowest frequencies of observation, and we start observing just the optically thin part of the radio spectrum. In some cases, even radiative losses for these adult radio sources. Of course, at some point, the activity stops. The lobes are no longer being replenished with the fresh plasma, and that's when slowly radiative losses start dominating. I think Beatrice showed a very nice and a bigger version of this plot, but it's basically the same thing that as radiative losses start to dominate, the spectra becomes steeper, and that's how you can identify these sources where the activity has switched off millions of years ago. And using this information, you can constrain how much time has it been since the lobes were last replenished with particles. We know from some population studies that about 9 to 10% of the radio AGN population have remnants. And in some cases, we can even observe a new phase of emission before the older emission is completed, faded below our detection limits. And those are the restarted sources, where you see a young phase at the center on galaxy scales, and then an older phase quite often much beyond the galaxy scale. So, right. So to give you an example of what they look like, this is some examples of a remnant source. You see these low surface brightness emission lobes from an older phase of activity, but when you look at the center with high resolution data, you see no active core up to your detection limit. Or if there are strong radiative losses, you see really steep spectra over 100 kiloparsec lobes that you see in these galaxies. So this is spectral index steeper than -1.8. From these studies, we have been able to constrain, for instance, for this source, the ages has been constrained to between 160 and 300 million years, depends on the curvature of the spectrum and the break and the assumptions about the magnetic fields. But typically, these remnants have these kind of features. They have amorphous, low surface brightness emission. There's usually no core, or they can be really ultra steep spectrum and even a spectral break. And then the other part of the life cycle, the other part is the restarted nature of these sources. Where if you look at the spectral index map again, you see this really steep spectrum on large scales, but where the core is, you start seeing much flatter spectral indices that are likely denoting a much fresher population of plasma. In the continuum, they've been observed for a very long time. The classic cases have been these two pairs of jets that you see in nearby radio AGN. And in some cases, you even see a very compact, bright core, but really low surface brightness emission barely being detected on large scales. And that also tells you that there's likely been restarted AGN here. So give you some more. These are the prototypical restarted sources that people usually see. These are all detected with the LOFAR. As Francesco mentioned, LOFAR is amazing for detecting these low surface brightness extended features. And then it also has the high resolution to go and look at the younger jets in the center with sub-arc second resolution. Although these here are VLA images in the high resolution that you see at the center, these younger jets. In some cases, we even see triple-double radio galaxies. There are radio galaxies where you see 3 pairs of jets, as you can see here. And at high resolution, you can see another pair. So there's only a handful of these objects known so far, but it's basically, I think, a matter of detection limits and how much you actually look for them. Right. So from whatever population studies have been done so far, people have been trying to constrain the understanding of the ages of these radio AGNs. So I'm not an expert on simulations, but people have used forward modeling with the semi-analytical simulations to get an idea of what the age distribution of radio AGN looks like. So in this case, you take what you know about the radio AGN population, like their morphology, their access ratios, luminosities, and the environments they live in. And then you try to get, for different assumptions of the age distribution, you try to get the fraction of restarted and remnant sources. That's what is shown here on the y-axis. And on the x-axis is different, the flux density and the redshift. And the idea here is that if you have an AGN, for instance, here in the black, that switches on for a constant amount of time, you get a certain distribution. If you have AGN where the age distribution has a power law, you get a different distribution. And the green data here is what we know from some complete samples of radio AGN about the fraction of restarted and remnant radio AGN. So you see that if you look at the data, the best matching distribution is for an inverse power law age distribution. We see that, which tells us that there are likely more short-lived sources when it comes to the radio AGN population than long-lived sources. And that can, at least so far, explain the restarted and remnant fractions we see. But this all depends on how we identify these restarted and remnant sources. There's a whole lot of different ways to identify. There's no one way is likely going to get you all the restarted and remnant sources. So the one study that I showed before used morphology and core prominence to identify restarted and remnant sources, but they didn't use the spectral information. And we found that if you have spectral information, you can actually pick up sources that were not identified as restarted before. And other people have actually found even better examples of it in literature. This is one source where you see where this is a nearby restarted radio galaxy at a redshifts of about 0.04. And using LOFAR, we were able to actually observe the large-scale emission and the small-scale emission at the same time. So this is a simultaneous observation with LOFAR. You can get both about 200 kiloparsec and sub-kiloparsec resolution data. And combining this with multi-frequency images, we could get spectral properties. And an interesting thing to note here is, if you look at this 100 kiloparsec lobe in the north, it has a remarkably homogeneous spectral index distribution. Now, as the plasma is traveling to larger distances, you would assume or expect the plasma to age as well. We find no strong evidence of that happening, which is telling you that either there is some reacceleration of particles here, and likely the jets haven't switched off for a very long time. Now, this was considered already a restarted radio AGN because of its morphology, because you see these 2 bright jets, and we could find that with the resolved spectral maps, spectral index maps using LOFAR and VLA, we could find absorbed jets here at the very 2 kiloparsec region in this source. So this source is a very shows you an example of an AGN where although there is restarted activity, the spectral signatures you see are not typical of an old aging plasma. This is likely telling you that the AGN has switched off for a very short amount of time and switched on again. And it's not the only source we see. Now there's, with LOFAR, there have been, and MWA, there have been many examples of such sources. I'm showing some here where you see a young source at the center, but on very large emission, on very large scales, you see really remarkably homogeneous spectral index distribution. So, which is telling you that the AGN has not switched off for a very long time. There is like kind of a flickering activity happening that is causing this, that is still fueling the outer lobes. Similarly, such similar flickering activity has also been seen in Fornax, but that was with integrated spectral indices. So of course, these sources do not fit the typical picture of restarted galaxies. So far, the population studies have used sources that can be very clearly identified as a restarted source, but if you just had the morphology of this source, you would not pick it up as a restarted AGN. So this tells us that studies in the future now need to include these sources as well to have a more complete census of the AGN duty cycle. And now with LOFAR, with LOLs and LOTs, as you heard before, the great overlap, I mean, they have in the sensitivity, it's actually possible to identify these in really wide fields. And that's something that I'm really looking forward to. Of course, there's another example or another possibility that the AGN never really switches off and gets the AGN jet flow is disrupted due to some interaction. But we do find in some cases that there is no evidence of a disrupted jet flow. The inner lobes connect to the outer lobes very neatly, and you can see a plasma channel connecting the two. Yeah. Right. Of course, there's also remnants that were actually sources that were classified as remnants before, based on their low surface brightness emission and lack of detection of a core. But with high resolution images, people have even found low level radio AGN in the center of these sources. So that's telling us that what we thought as remnants before might not all be remnants. There might be still be some radio AGN at the center of these sources. So with all of this, this is probably a more updated picture of the radio AGN life cycle, where you don't just have sources going from young to adult to remnants, but even young sources dying very quickly, not growing to become the large-scale radio AGN. Sources that are restarting after very short time scales, like the one we saw before. But of course, the ones that have been identified before that restart after 300 or 200 million years. So I mean, there was this discussion on duty cycle of AGN sometime during the week. So, I mean, from the radio perspective, I think now is when we actually can get a better constraint than ever before on the duty cycle of radio AGN. Right. So, yeah. But of course, what we are very interested in is in knowing what this life cycle means for feedback. If the radio AGN is going through different phases, does it change how it affects the host galaxy's ISM? So to sort of look at that from a statistical point of view, we constructed a radio AGN sample up to redshifts of 0.8. We use the multi-frequency radio data to sort of identify these sources in different stages of evolution. So we take our sample, we split it into peak spectrum sources and non-peak spectrum sources. This is a very crude distinction, but given the sample size, this is the best we could do so far. So as I said before, if you have a peak radio spectrum, it's likely a group of sources that are younger, at a younger stage. And if you have a non-peaked optically thin spectrum, they're likely at a more evolved stage. So we combine 3 radio surveys. I think I'm just going to introduce all 3 of these lots first in VLSS. And you can construct a color plot of spectral indices. So on the x-axis is the low frequency spectral index. On the y-axis is the high frequency spectral index. Essentially, depending on a source's position on this diagram, you can get an idea of its radiospectral shape. So if a source lies here, it has a peaked radio spectrum, likely a young source at the center. And if a source lies here, it has an optically thin radio spectrum. The great thing about these surveys is that because of the 6 arcsecond resolution, at least in the nearby universe, we can identify a young source at the center of really like hundreds of 500 kiloparsec radio AGN. So all this emission here you see, there's a young source here at the center, but all this extended emission only been picked up by LOFAR, telling us that the picture for these compact young sources is actually more complicated. A lot of them will actually have extended emission as well on hundreds of kiloparsec scales. So that's also worth looking at in terms of the feedback they have. Okay, so if you just look at the average O3 profiles, which we get from SDSS, and do a quick stack, you see as you move from this region where the most peaked spectrum sources lie to sort of sources with an intermediate frequency peak and then the non-peak sources, you start seeing that the broad level emission goes down. The wings of the O3 profile start getting weaker, which is already telling you that the gas is likely less disturbed as you're moving to more evolved sources. Of course, you can control for different source luminosities as well. So here we are comparing the same peaked and non-peaked spectrum sources, but controlling for radioluminosity on the x-axis and O3 luminosity on the y-axis. These sources are matched in their host galaxy properties and their location on the BPT diagram, for whatever sources we have, their Balmer decrement as well. So really, we've tried to make sure that the only thing different between these 2 sources is their radiospectral shape. The color of every square shows the average velocity dispersion, and the fraction shows the number of sources that have an average velocity dispersion 3 sigma larger than the stellar velocity dispersion in that bin. And you can see that sources with a peak in the radio spectrum have consistently larger or broader O3 profiles, but most of them lie at the higher luminosity end. So it's really above the 10 to the power 24, 25 watts per hertz where we are seeing the strongest difference between radio AGN at different stages of evolution. And I mean, once you normalize all the O3 velocity dispersions for stellar velocity dispersions to control as much as you can for gravitational motion, you still see similar results. We find that the young and powerful jets still seem to have the strongest impact on ionized gas. And we know that this young phase typically lasts for only a few million years, mostly less than a million years from spectral age arguments and dynamical age modeling. So this is likely telling us that on average, the strongest impact in these powerful sources is perhaps only for a fraction of the radio AGN lifetime when we're looking at the central region. Of course, this is only on average for a population of sources. You might still find some non-peak sources that have really disturbed gas on different scales. But this looks like that the most disturbed gas is only present when the jets are young. So I just want to mention that there have been hydrodynamical simulations that have tried to track the changing impact of jet ISM interaction. This is a very nice simulation from Nakshi et al., which shows how jets inclined into the galaxy, the gas disk, will change what you observe in terms of the O3 flux distribution and the kinematics as they grow from really the sub-kiloparsec scales to beyond the galaxy scale disk. These are 3 different stages of the jet life cycle, and you can see that the O3 flux distribution and the kinematics, the O3 kinematics distribution also changes. So we are trying to sort of compare, or we are currently performing a study to sort of compare our results with this using GMOS data for the sample I showed before, to see if we can track the changes in the gas kinematics, morphology, and excitation for sources at different stages of evolution. But of course, as I said, the radio agent that I showed before, they're all really the more powerful sources that we know, mostly above 10 to the power 24 watts per hertz. And as we know from studies of LOFAR radio AGN fractions in galaxies, this is likely only placing or likely only covering a very small fraction of the parameter space. So this was a very nice study by Sabelder et al. In 2019, which I think was shown before as well, which shows that as you go to really low and low radioluminosities with LOFAR, you find more and more radio AGN in galaxies, especially in the most massive galaxies. You might reach a point where you find some level of radio AGN in all massive galaxies. But of course, the question is that is the radioluminosity or is the power of the jets in such low radioluminosity really relevant for, or does it have any significant impact on the gas? So should we, like it was mentioned in the discussion, that should we really care what these low power jets are doing in these galaxies? So we have tried to look at that using spatially resolved data with MANGA. So MANGA was mentioned once before a couple of weeks ago or a couple of days ago by Arjun. And MANGA is a sample of nearby star-forming galaxies, so it's not really suited for the most powerful radio AGN. But what it does have is a lot of low power radio AGN, so you can really look at their kinematics. So we combine MANGA with LOTS and FIRST to identify a sample of almost 800 radio AGN. About half of them have detections, O3 detections in MANGA. So we can look at the gas. Here you see just where they lie on the parameter space of O3 and 1.4 gigahertz radioluminosities. You see blue sources are sources classified as an optical AGN. So just using the BPT and a cut on the equivalent width of the H alpha. Red sources are sources that only have a radio AGN, so they do not have an AGN classification on the BPT. And then black points are sources that have a radio AGN, but also an optical AGN classification on the BPT. And the idea here is so that if we can sort of have these different kinds of AGN and compare with the same data, can we get an idea of the role of jets and radiation in the same group of sources? The problem with at such low radioluminosities is that you can never be sure that the radio AGN you see, it's hard to be sure that the radio AGN you see at such low radioluminosities has a jet. That's still a matter of debate, and we have heard about it before as well. And you can see here that these shaded regions actually show two models that model the expected radioluminosity from shocks driven by winds in the ISM. And if you look at the sources that have both radio and optical AGN, the black points, about half of them can be explained by the radioluminosities, at least energetically, can be explained by shocks causing the radio emission. So if you now I'll just quickly show the radial profiles of the sources. So yeah, the idea was to take all these sources and extract their radial profiles of O3 line widths, but also normalize pixel-wise every O3 velocity width with the stellar velocity width, to sort of correct for effects of inclination or blending of lines, and yeah, get an idea of what the velocity field itself, velocity field of the galaxy is itself. So if we do that, and we compare different AGN groups, so the black line you see here is sources that have both radio and optical AGN. Blue only have an optical AGN, red have a radio AGN, and there's a control sample of similar galaxy mass and morphology and Balmer decrement and stuff. So it looks like you would think that the radio and optical AGN have the most disturbed gas in the central region. The x-axis here is radial distance in terms of effective radius. And then radio and optical AGN seem to have similar effect in the central region, but, and the least effect, of course, when there's no AGN. But if you correct for the for the cellular velocity dispersion, you find that the difference still exists, but only in the central region. Like if you, the bottom panel here shows p-values of the differences at every points between the any two groups. And we find that only when you have a radio and optical AGN simultaneously in a source, you find the most disturbed gas at low in these low to moderate luminosity systems. But of course, because we have low luminosity systems as well, we can look at just this low luminosity system to see what we find. And we find that the difference is not very clear anymore. Now we are restricting our sources to very low radioluminosity AGN. And when you go to such low radioluminosities, the differences in the kinematics for when you have a radio AGN and when you don't have a radio AGN doesn't seem to be that significant. Of course, so this might point towards the fact that maybe at such low radioluminosities, you wouldn't see very disturbed ionized gas. So maybe we should not be looking for the most disturbed ionized gas or using that as a proxy for feedback when we are talking about low radioluminosity AGN. Right. Okay. So I think almost. Yeah. Okay. So this is the summary. So with new survey data, we are now finding that the radio AGN life cycle is richer than we thought in the past. There are sources at different ages in the radio AGN population that need to be accounted for when we are trying to understand the duty cycle. Then that affects how we include AGN feedback in the simulations. And we need, but this requires multiple approaches simultaneously to identify, to get a complete sample of restarted AGN and get a full census of the duty cycle. We also find that the feedback in the youngest sources is strongest on average compared to when jets are more evolved in the nearby universe. And when we're looking at the low to moderate luminosity systems in the nearby universe, the impact of the low luminosity jets on average doesn't seem to be very significant or very different from when you just have an optical AGN or yeah. So yeah, with that, I will end and take any questions. Thank you.
Can you go back to the plot where you showed manga matched with? No, yeah, this one. I was just wondering how many of these radio sources came from lots and how many came from first.
So with lots, we have about 500 sources and about 300 from first.
And you use the fluxes from first?
Well, yeah. So the fluxes are taken from this. For the first sources, we extrapolated the low frequency fluxes to 1.4 gigahertz, and then the fluxes are all taken from the first data. So it's sort of to compare only the luminosities of the central region, these sources, because the integrated fluxes on larger scale, I mean, it's mostly beyond the galaxy, and then the O3 luminosity you have is really a 3 arcsecond fiber on the host galaxy. So it's sort of compare on similar scales, we took only first fluxes at the central region.
Another naive question that you're talking about the duty cycle. So it's mainly about that you find one and you find another one, right? I was have a different question is asking when you have launched this jet and it's go to outer skirt or whatever, and it's get fended out, right? When from its launching to almost you cannot see it, how long this time will be, roughly?
You mean like how long has it been since the jet was launched?
Yes, it's launched and you cannot see it. It will dissolve into the CGM or something like that, right? So what the time scale?
Yeah, so you can only actually get timescales when you see the large scale emission as well. And you try to get a constraint from the spectral age. So you assume that, okay, whatever the acceleration has happened in the lobe happened when the jet was launched and it injected fresh plasma into the lobes. And from the spectra, you try to get a constraint on how old this plasma is. But of course, There's-
How long it can last?
Oh, it depends on, it changes from sources to sources. Typically, it's 10 to 100 million years, but it depends on the physical conditions as well. If you have like a bunch of electrons emitting in synchrotron, a stronger magnetic field will make it age faster. A lower magnetic field will keep it aging, keep the aging lower. So it really depends on the physical conditions, but spectral ages are anywhere between 10 to 100 million years to 100 million years. I mean, remnants people have even seen larger, slightly larger ages as well. Thanks.
I have a question about the host gases. So I saw some old radio gases, the time scale is about several hundred million years, which is close to, I guess, the post-starburst phase we mentioned, we found in the galaxies. Have you found any post-star features in those host gases?
No, I have not looked at that, but it is it is one thing that we have been thinking of doing is to look at these not just remnants but restarted sources and look at their star formation histories to see if we can find any correlation between the presence of activity for hundreds of million years and any recent star formation from the absorption spectra.